So, welcome back to lectures on engineering mathematics 2, and today we will begin with module number 2, that is on complex analysis. So, this is lecture number 1 on complex numbers and functions. So, today we will cover we will introduce the complex number. So, this is going to be a review because you are familiar with the complex number by now. So, this modulus and the argument of a complex number will go through, and some properties of the modulus we will cover, and then we will come to the complex functions, and in particular we will be talking about what are the complex functions and their limit. So, coming back to the complex numbers. So, a complex number we usually denote it is by z. This is written in the form z equal to a plus I b, or equivalently we also write z is equal to a plus b I. So, I b or b I, where these a and b are the real numbers and I is called the imaginary number, which satisfies I square is equal to minus 1. So, these real numbers a and b are called real. So, the a is called the real and the b is called the imaginary part of z respectively. So, all complex numbers will be denoted by this C, that is a set of all complex number. And just to show this geometrically, so there are two ways. One we can think is as a point in this two dimensional plane. So, this is what we call here in this connection or in this context the real axis, and this y axis we will be calling as the imaginary axis. So, here we have a the component in the real axis and the b, which is the imaginary part of z. We have this distance from the real axis to this point b. So, this is a point in this two dimensional plane. We can treat it as a b, which is the complex number we have denoted by this a plus I b. The other way we can actually geometrically represent this would be in a vector setting, which vector we have already covered. So, this a b, this point, or this z is equal to a plus I b, we can think as a vector pointing to this point a b, that means a I plus b j. So, I and j are the unit vectors in the direction of this x axis and y axis. So, we can also define this in as a vector in a plane, or we can define this complex number as a point in a plane. Well, so some arithmetic on complex numbers to get familiar again, or just to recall some of the properties. So, equality means if a plus b is equal to c plus this I, this imaginary number I d, then this is only possible when we have both the real parts, that is that means a equal to c, and also this imaginary part, that is b equal to d. So, these two numbers are equal if we have a equal to c and b is equal to d. The addition we can define again, we have to add the complex the real part as well as the imaginary part separately. So, if we have two numbers here, a plus I b and then c plus I d, so their sum will be the addition of the real number, that will form a real part of the addition, and this I b will be added to this I d. So, that will form the imaginary part here. So, a plus c and plus I b plus d, that will be the addition. So, coming back to the multiplication, we have to just consider that this I square is equal to minus 1, and we will go with the product as we do for polynomials. That means, a plus I b and c plus I d, if we want to multiply, then we will do the usual multiplication we follow in case of the polynomials. So, a will be multiplied by c. So, we have AC, A will be multiplied by ID. So, we have AD and with the I, then we have I with this IB with C. So, we have this product here BC product with I, and also we have IB and then we have ID there. So, this is I square multiplied by this BD, and I square is minus 1. So, this is like minus BD. So, we can write down AC minus BD, AC minus BD, and with this I we have AD and BC. So, it is a very simple usual multiplication once we just consider that this I square will be replaced by minus 1. So, similarly, we can define the multiplication we have defined already. We can also define the product, which we will come little later to define that. So, first let me just introduce this complex conjugate, because that is another very important part here to be discussed. So, the complex conjugate of this Z is equal to A plus IB, the number A plus IB is defined as, the conjugate means this I will be replaced this by minus I. So, that means we have the complex conjugate A minus IB. This is the complex conjugate of the number Z, A plus IB. This is what we call this complex conjugate. Now, what are the modulus and the argument of a complex number? So, let us suppose this is the point here x y, or the number this x plus I y in the plane x axis, this is a y axis here. So, this is the distance here x, and this is the distance here y. Therefore, this point is x plus I y or x comma y, whatever ways we define this here. So, the distance from the origin to this point will be denoted by this number r, which is going to be since this is x and this is y here, or this point is x comma y. So, from this 0 0 to x comma y, the distance will be x square plus y square and the square root. So, here this r, the distance from the origin to this one is important, and then this theta. So, just recall how do we characterize in the polar coordinates. So, similarly, we have here this is the theta, the angle from this x axis, and then we have this distance r. These are the two numbers which with the help of these two numbers we can again define the given complex number. So, now this number r is called the modulus of the complex number, and the modulus of this x plus I y is denoted by this sign absolute value x plus I y, and this is defined as the square root x square plus y square, as I discussed, that this r is the distance from origin to this point, which is nothing but the square root x square plus y square. So, r is x square plus y square square root, and this is what written here, this is the modulus of this complex number x plus I y. The angle theta, which is given here, this line makes from with the x axis, this is called the argument of z, and this argument is denoted by arg z, and it is defined as that theta is the argument of z. Theta, we know now what is the theta, that is the angle here, this axis, this line is making with the x axis. So, theta is the argument, and since this is the distance x here, this is the y. So, we have tan theta is equal to y over x. This relation must hold for this theta, and since if this is the angle theta, if we go again with 2 pi, if we add 2 pi, we will be back to this angle theta. So, if theta is the argument, then theta plus 2 pi is also the argument, or theta into, so theta plus this n into 2 pi, n is any integer you take. So, if this theta is the argument, theta plus 2 pi into n will be also the argument, that will also satisfy this tan theta is equal to y by x, and representing the same angle with this rotation. So, there are infinitely many such values of theta, but we will just choose between this minus pi to pi. So, if theta is is from this x axis to up to this pi here, the angle is coming here from 0 to pi we will take, and then otherwise in this direction we will go with this. So, from here to here we will cover with the pi 0 to pi, and then in this direction we will cover with minus 0 to pi. So, any theta we can have between this minus pi to pi, and this is what we called the principal value. So, this theta which is between minus pi to pi is called the argument. So, the principal value of argument, which is usually denoted by this big A R G Z. So, this is what we call the principal among infinitely many values of theta, because as we discussed that we can add 2 pi, we can add 4 pi, again we are back to the same angle. So, among all these, if we choose the one which lies between this minus pi to pi, we will call this as principal value of argument of z. So, that is going to be just the unique value. Well, so the polar form of complex number we will define with the help of this argument and this theta z. So, not that this x, because this is the x distance here and this is the y distance. So, we can have this relation that x is equal to r cos theta and the y is this r sin theta. From this triangle we can identify this relation that x is r cos theta and y is r sin theta. Then this z equal to x plus I y can be written as, so with this relation we can write down z is equal to x plus I y, x is r cos theta, y is r sin theta, and if we take this r common we have cos theta plus this I sin theta. This is the trigonometric form we call of the complex number z, which is represented here by this x plus I y. So, the trigonometric form will be r into cos theta plus I sin theta, or we can replace this cos theta plus I sin theta with this r into e power I theta. So, e power I theta, this Euler identity, we have the cos theta plus I sin theta. So, we can write this as r e power I theta, and then this is also called the polar form or the exponential form of the complex number. So, we have the three form, the standard one, z is equal to x plus I y, then we have the trigonometric form, and then we have the polar or the exponential form, which is written here in r e power I theta, the trigonometric form r cos theta plus I sin theta, and then we have the usual in the Cartesian coordinates. So, x plus I y. Okay, so, now we are familiar with the polar form of a complex number, the modulus, the argument. So, we can go through some properties of complex numbers, which will be used later. So, again this is to recall, because many of these properties are already discussed in the complex numbers when we begin to learn. So, here this very nice important property we have that z and the, if we take its conjugate. So, this is equal to the absolute value of z square. So, this can be easily seen that if we take z is equal to I a plus I b, for instance, this number, and we know z is equal to a minus I b, and if we look at this product here z bar, that is going to be a plus I b and the product with a minus I b. And if we do this product, so it is a plus I b, a minus I b, that means we have a square minus I b whole square. So, a square and then minus I square. So, I square will be 1. So, we have the plus here b square. So, that means this is a square plus b square, and if we look at the other side, that is the modulus z is given, which is once the number is a plus I b, the modulus z is a square plus b square. That means the this modulus z square is a square plus b square. So, we do see that both are equal, that means z bar is equal to a square plus b square, and that is equal to mod z whole square. So, these two are equal. Well, so we will erase this here now. Okay. So, the next we have this property that the absolute value of z equal to 0, which is only possible when this z equal to 0, or if z is equal to 0, we have the absolute value must be 0. So, this is clear, we have already seen what is the argument. So, argument was a distance there from the origin to that point, and that will be 0 if exactly you are at the origin. So, if you are just away from the origin, so there will be some distance, and that cannot be 0. So, the 0 z equal to 0 implies that the absolute value is 0, and the absolute value of complex number 0 implies that this number is 0. So, here we have the absolute value z equal to the z bar. So, this is also trivial because we have z a plus I b, for instance, and this if we take the absolute value, this is a square plus b square and the square root, and similarly if we take the conjugate, that is a minus this b I, and if we take now the absolute value. So, this is going to be the same, a square plus b square, this square and plus minus b square you can say, but it is b square only. So, these two values are same. So, this the z, the absolute value of z or the modulus of z is equal to the modulus of its conjugate. Regarding this property, so the again we can prove similarly, because if you take the two number again a plus I b and a minus I b as your z 2, and if we add the two z 1 plus z 2. So, here let us say the c and d. So, z 1 is a plus I b, and then we have c plus I d. So, again we will take. So, a plus I b and the z 2 we are talking about the new number. So, c plus I d, and if we add the 2. So, z 1 plus z 2 we know how to add. So, a plus c, and then we have I and b plus d. Now, we are talking about its arguments. So, we can take the argument here, that is this is square plus this is square and the square root we are talking about, and similarly we can get the individual one here, that is just the absolute value. So, we can take the absolute value of this. So, this plus will be becoming just the minus there, and when we talk about the individual conjugates. So, again we have a minus I b and then plus the c minus I d, and the result would be the same, because we have a plus c and then minus I, if I take common here b and plus d. So, this and this is the same. So, therefore, we have the conjugate of z 1 plus z 2 equal to conjugate of z 1 plus conjugate of z 2. Similarly, we can also prove that the z 1 z 2, if we have the product. So, again z 1 and z 2 the conjugate, one can prove this. Also for the minus, one can prove that z 1 minus z 2 the conjugate is going to be z 1 conjugate minus z 2 conjugate. So, these two also we can easily prove, as we have done for the plus. Coming to the next property. So, we have the product here z 1 z 2 and equal to this modulus z 1 and this modulus z 2. So, concerning this property, so we will take z 1 for instance in the polar form. So, r 1 or in the trigonometric form. So, cos theta 1 plus I sin theta 1, and the z 2 we can take r 2 and then cos theta 2 plus I sin theta 2. So, these are the two different numbers z 1 and z 2, and we are talking about the product. So, z 1 z 2, this product we can talk here. So, this is r 1 r 2, this product will come, and the product of the two here. So, that will be cos theta 1, then we have cos theta 2, and then all real I will consider first. So, this I will be minus. So, minus sin theta 1 and sin theta 2 will be there. Then we have with the I here sin theta 1 and cos. So, sin theta 1 cos theta 2, then we will have plus. So, here cos theta 1 cos theta 1 and sin theta 2. So, this we will get out of the product. That means, we have R 1 R 2, and if we combine this trigonometric identity. So, we have cos theta 1 and this plus this theta 2, and then we have plus I, and this is sin theta 1 plus theta 2. So, what do we get out of it? That so, we have this relation that Z 1 Z 2 is equal to R 1 R 2 and cos theta 1 plus theta 2 I times sin theta 1 plus theta 2. Now, looking at what is the, so this Z 1 Z 2 is another complex number, which is again in this form R cos theta plus I sin theta. So, we can easily look into this now, that the Z 1 Z 2 the absolute value, the modulus of this is going to be just R 1 R 2, because this is the modulus part. You have R cos theta plus I sin theta. So, then we have this R 1 R 2, and R 1 R 2 was nothing but the absolute absolute value of Z 1 and this Z 2, or the modulus of Z 1 Z 2. So, this is proved now that modulus Z 1 Z 2 is equal to modulus Z 1 plus modulus Z 2 with this relation. The another property which again we can directly look at, that is the argument Z 1 Z 2. So, here again from this relation we can find out, we can realize that this Z 1 Z 2 is equal to this the argument. So, the argument of Z 1 Z 2 again from this relation is nothing but the theta 1 plus theta 2, and then from here theta 1 plus theta 2 we know already that the theta 1 was the argument of Z 1 and the theta 2 was the argument of Z 2. So, we have this relation as well. So, these are the two important identities which may be used later, and this relation here plays a crucial role, that the Z 1 Z 2 is equal to R 1 R 2 and theta 1, this cos theta 1 plus theta 2 I sin theta 1 theta 2. Indeed, if Z 1 Z 2 are same, so we will get here like Z, for instance. So, Z square will be R square and cos 2 theta plus I sin 2 theta, or we can generalize these results when we have Z power n, then here R power n cos n theta plus I sin n theta also we will get instead of this. So, this equality we can generalize, and we can refer to some other properties based on this relation. So, let us moving further now. Yeah, this is exactly what I was talking about from this last identity, the product of the two number which were written in trigonometric form. We can directly conclude from there that Z power n. So, we have instead of Z 1 Z 2 now the same number Z. So, here the product of R was coming. So, now we have R power n, because we are talking about n numbers, and cos. So, there it was theta 1 plus theta 2 for two numbers. We have the same number which is multiplied n times. So, here n theta, and then we have again n theta there. So, this is the identity which is just coming from the previous one, and this is of course the implication of the above result, because if we take the modulus of this. So, modulus of this is nothing but the R power n, and R is the modulus of Z. So, this is just the coming from the above identity, or similarly the argument of Z power n if we want to get. So, we have this n theta, n and theta is the argument of Z. So, this is also directly coming from this identity. If we talk about the Z 1 divided by Z 2, the argument Z 1 divided by argument Z 2 will be appearing here. The idea is again same. So, we can take that trigonometric form. So, Z 1 divided by Z 2, we have R 1, we had there cos theta 1 plus I sin theta 1 and then we have here r 2 and then cos theta 2 plus I sin theta 2. So, with this relation we can again rewrite this. So, we can multiply here the divide by the conjugate, and also we can multiply by its conjugate. So, when we divide here by this conjugate here cos theta minus I sin theta. So, what will happen? So, if we do so, so just one more step. So, cos theta 1 plus this I sin theta 1, and if we multiply by this conjugate, that means cos theta 2 minus I sin theta 2 and divided by. So, here it will become with minus. So, cos theta whole square and then minus I square sin theta whole square. So, this minus I square will be again this 1. So, I square is minus 1. So, that will be just 1 there, and then we have r 2, and we can multiply there the numerator part. What we will get finally, that r 1 r 2 is nothing but we have cos theta 1 minus theta 2 plus this I sin and theta 1 minus theta 2. So, this relation we will get, and this we can directly now get that the argument or the modulus of this z 1 divided by z 2 is nothing but the r 1 by r 2. R 1 was the modulus of z 1, r 2 the modulus of z 2. So, we have proved this identity, and similarly we can also look at this one where argument z 1 over z 2 we are looking now. So, argument is theta 1 minus theta 2. So, theta 1 is the argument of z 1 and then the argument of z 2. So, many such properties we can just prove with the knowledge of this multiplication we have just learned there. So, we will directly now go to the function, the complex function, and some of these its properties will be discussed. So, before that we have to talk about the neighborhood of a point. So, the neighborhood in the circular domain is a circular domain about this z 0, and whose radius we have taken this delta. So, this is called the delta neighborhood. So, it is a circular region around this z 0 with radius delta. It is a disk here, and this is what we call the neighborhood of a point, the delta neighborhood of a point. The delta is the radius. Usually we talk about a very small number delta which define the neighborhood of this point. So, this boundary here, the z minus z 0 is equal to lambda, the inner part is z minus z 0 less than delta, because the distance to any point there inside it is less than delta, any point we can take, and when we are on the boundary this distance is equal to delta. Therefore, this is this defines the boundary, the circle z minus z 0 is equal to delta. So, another could be the rectangular domain. For some convenience sometimes we can also think about the rectangular domain. So, this is the neighborhood of this point z 0, a rectangular one. A b is this distance and d minus c. So, b minus a and d minus c. So, around this we have a rectangle with these distances here from a to b and then there c to d. So, that could be also a rectangular domain which is defined here, but the circular domain is more common and will be used frequently whenever we are talking about the neighborhood. So, any circular domain or rectangular domain around a point is called its neighborhood. That is in a simple words we can think of a neighborhood. Now, defining the function of a complex variable. So, let us suppose this d is a set of complex number. So, it is a part of the full complex number C, and a function f is defined on d, which is usually we call the domain. When the function is defined on this d, is a rule that assigns to each value of z in this set d a complex, another complex number w. So, this f is taking as an input from this complex number and again producing a complex number. So, that is the function, a mapping from complex number to a complex number. Usually we denote this w is equal to f z, or we write it as f. So, x I y it is the input to this function, the complex number, and then we are getting again a complex number u, which is a function of x y plus I v x y. So, from complex number to complex number, that is the mapping this function is doing now. So, for example, w is a z square. If we talk about w is z square, so its f z is here z square, and if we write in the expanded form, so z is square, z is x plus I y, and if we perform this product, we are getting this x square minus y square plus 2 x y I. So, here we have this u is x square minus y square, this function, and v is the function 2 x y. So, we can always write in u plus I y form a given function, or in this compact the z square form. Okay, coming to the limit of a function of a complex variable, function of a complex variable. So, f z is defined and is a single valued in the neighborhood of this z is equal to z 0. So, the function is defined in the neighborhood of z 0 point, and we can talk about the limit now. So, let this w 0 be a complex number such that the limit of this f z as z approaches to the point z 0, we are getting the complex number w naught. What does that mean? If and only if for a given epsilon. So, this is more mathematical definition we give for the limits. So, if for a given epsilon there exists a delta such that this f z minus w, the difference between this f z and minus w naught, the distance between the two, is less than epsilon whenever we take the z from the neighborhood of this z naught. So, the difference the distance between z and minus z 0 is less than delta naught, the distance between this is less than epsilon. So, for given epsilon, for any given epsilon, if for any given epsilon we can find such a neighborhood, then we call that this is the limit. So, this is exactly what we consider this limit in the real analysis. So, there is no difference, and we call this w naught the limit of this f x f z indeed when z approaches to z naught, or we call in more simple words that this limit f z, z approaches to z naught is w naught if the difference in absolute value of this f z and w naught can be made arbitrarily small by choosing this z close to z naught. So, we have the two neighborhoods here, the one is around this z naught point with delta radius, and there is another in u v. So, here we have x y, let us say here we have the function f z, we are talking about the w naught, and this is the neighborhood, this epsilon neighborhood. So, for any given epsilon however small, if we can find a neighborhood here around this z naught, so that this f z any point in this neighborhood assigns the values in the neighborhood of this w naught, then we call that this is the limit of this function. Well, so, limit in terms of real and imaginary parts of a complex number we can define. So, if f z is u x y plus I v x y, and this z naught is x naught plus y naught, then we can say that f z as z approaches to z naught is u naught plus I v naught. And what is this u naught and v naught? These are the limits of this u and v as x y approaches to x naught y naught. So, this u naught is this limit of function of two variables, and this is the limit for this v function as x y approaches to x naught y naught. So, for example, if we consider we want to get this limit z approaches to 2 minus 3 I of this absolute value of z. So, we know the absolute value of z is x square plus I y square. So, this is only the real part, and we will just compute that what will happen when x y approaches to 2 minus 3 of this function, which is straightforward. So, 4 and plus 9, that is square root 13, that is the limit of this absolute value of z as z approaches to 2 minus 3. So, when z approaches to 3, we have this z square 4 z minus 21, divided by the z minus 3 we want to get. So, this is another approach we can follow. So, we observe that the numerator can be written as z minus 3 and z plus 7 divided by this z minus 3. So, this z minus 3 gets cancelled, and when z approaches to 3, this z plus 7 is getting just the value 10. So, we have this limit as 10 for this given function. So, these are the references we have used for preparing this lecture. And just to conclude, we have learnt that how to represent a complex number, and there were two ways we have discussed, that we can think as a vector in a plane, or we can think as a point in a two dimensional plane. We have also seen this trigonometric representation of the given function, and as well as this exponential representation of a complex number. And then we discussed about the complex function, w function of the z f. So, this may be also expanded as a u x y and this I v x y, and f the z is written as x plus I y. So, in this form, and we have also discussed that what do we mean by the limit of a complex function. So, f z, when z approaches to z 0, we have w naught. So, we have also seen the epsilon delta definition and its physical interpretation. So, that is all for this lecture, and thank you for your attention.